Good morning all. In today's session we are going to study about the overall dimensions of transformer. In the last video session we have studied about the design of transformer cores. There we have also studied the various types of ratios, including the core area factor in the case of a square core, rectangular core and cruciform core. Let's begin with window area. In a transformer, this portion is actually representing the window of the transformer. These two are actually the transformer cores and these two are actually the transformer yokes. The window area can be easily obtained by multiplying the height of window with the width of window. You are quite familiar with the term window space factor. We have studied them during the derivation of output equation in both single phase as well as three phase transformer. It is represented as kW and it is defined as the ratio of conductor area which is present in the window to the total area of this window. The total area of this window is given here, that is height of window into width of window. So from the relation of window space factor I can write the area of window as total conductor area and divided by window space factor. The total conductor area is indicated as AC. In the case of a single phase core type transformer, both the primary winding and secondary winding are wound over the two limbs of the transformer. This is actually one limb and this is actually the other limb. Or we can say both the primary winding and secondary winding are wound over the cores. This is one core and this is the other core. Both are wound over the cores of the transformer. Therefore, the copper area which is present in this window can be written as TP AP plus TS AS. TP is actually the primary turns and AP is actually the area of conductor in primary winding. Similarly, TS and AS corresponds to the secondary winding. This relation is also quite familiar for you. You have studied about them in the derivation of output equation in both single phase transformer as well as three phase transformer. Instead of AP we can substitute as IP by del. The same relation which we have written there is repeated here. So finally we can write AC as 2 times ampere turns divided by del, where del is actually the current density. Similarly, in the case of three phase transformer, we can obtain the relation for AC as 4 times ampere turns divided by del. You may refer the first video of transformer to get a clear idea about this. If you remember it, then it's well and good. So there are two methods by which we can calculate the window area. One is by the product of height of window and width of window, and the second one is from the window space factor kW. Usually in the case of the transformer, the ratio of height to width is selected between 2 to 4. This is done in order to achieve a suitable arrangement of height and width of the transformer. Next we are going to discuss about the window space factor. Just like we mentioned in the previous slide, it is defined as the ratio of copper area in the window to the total window area. The copper area present in the window has a dependency over the insulation which is provided over the conductors, that is primary winding and secondary winding, which further has a dependency on the voltage rating and output rating of the transformer. Hence we can say that the copper area which is present in the window is having dependency upon the voltage rating as well as output rating of the transformer. The empirical formulas which are used for window space factor are given here, based upon the various ratings of the transformer. In this relation, this kV is indicating the voltage of high voltage winding in kilovolt. A transformer will be having both low voltage winding as well as high voltage winding. So this kV is indicating the voltage of high voltage winding in kilovolts. Next we are going to see the overall dimensions of the transformer. The indications, the standard indications which are used are represented here. We will begin with the dimensions of single phase core type transformer. The diagram of single phase core type transformers are given here. This is representing the vertical cross section and this one is representing the horizontal cross section of the transformer. This portion is indicating the window of the transformer. These two are the cores and these are the limbs. Please be clear that this diagram is representing the vertical cross section and this one is indicating the horizontal cross section. In fact, we can say that this is actually a horizontal cross section's top view. This portion is indicating the yoke of transformer and the height of yoke is indicated as HY. Similarly, this portion is also representing the yoke of transformer and its height is also given here, hy. The balance portion, this one, if you are seeing, this is actually the window of the transformer and the height of the window is indicated as hw. So the overall height of the transformer H can be written as hw plus hy plus hy. That is H is equal to hw plus 2hy. That relation is mentioned here. Next we have to find the overall width of the transformer core. The overall width of the transformer core is indicated here as W. The center to center distance between two cores, this is actually the one core and this is the second core, and their center to center distance is indicated as capital D. This shaded portion is indicating the primary winding and secondary windings. Both these shaded portions are indicating the primary and secondary windings associated with both the cores. This much portion is indicating the circumscribing circle. If you see the same in the horizontal cross section, you will be able to see this is indicating the circumscribing circle, and this portion is actually the windings. The diameter of the circumscribing circle is indicated as small d. While looking into the width of the window, you must be very clear that the width of the window will be taken from this particular point to this particular point. See, this line is extended downwards and from here till here. It is not from this point to this point. The width of the window is actually indicating the portions between these two circumscribing circles. See, between this circumscribing circle and this circumscribing circle, this portion is actually representing the width of the window. Now you can easily write the relation between dWw and small d. This d is actually the center to center distance between two cores, and ww is actually the width of window, and d is the diameter of circumscribing circle. So from here it's very clear that the capital D is equal to the sum of width of window and d by 2. So altogether I can write capital D is equal to ww plus d by 2 plus d by 2, or else I can write capital D is equal to ww plus d. That relation is mentioned here. From the horizontal cross-sectional view, it's very clear that the core which is used here is a two-stepped one, or we can also say it as cruciform core, and this portion is indicating the width of largest stamping and it is indicated as small a, and this will be indicating the depth of yoke. The depth of yoke in this case is same as that of the width of largest stamping, that is small a. Now while writing the relation for overall width of the transformer frame, the overall width of the transformer frame can be written as the sum of the center to center distance between two cores and width of largest stamping, because the width of the transformer core is from this point to this point. D will be indicating the distance from the midpoint of this core to the midpoint of this core. So we are left with only this much portion. This is actually the whole length is A. The whole length of this stamping is A. So definitely the half of this length will be A by 2, and here also half of this length will be A by 2, and the center to center distance is capital D. So we can find the overall width of the transformer by adding the half of the width, that is A by 2 plus D plus A by 2, that is D plus A. Now we will write the relation for area of yoke. This portion is indicating the yoke and its height is given here hy, and the depth of the yoke, as we have already mentioned from the horizontal cross-sectional view, that the depth of the yoke is same as that of the width of the largest stamping, and the width of the largest stamping is indicated as small a. That relation is mentioned here. Hence we can write the area of yoke as depth of the yoke into height of the yoke, where depth of the yoke can be written as small a. This relation, that is depth of yoke is equal to the width of the largest stamping, is applicable only in the case of square and stepped cores, while in the case of a rectangular core, the depth of the yoke will be same as that of the depth of the core. In the diagram which is shown here, it's very clear that the cores which are used here are of cruciform cores or stepped. The width over one limb, that is the distance between this point and this point, can be easily found out by finding the outer diameter of the high voltage winding. The width over two limbs, that is the distance between this point and this point, can be found out by adding d. D is actually the center to center distance between the two cores, and half the diameter of outer high voltage winding and half the diameter of outer high voltage winding. Or else I can say that the distance between this point and this point is the sum of d and outer diameters of high voltage winding. That relation is mentioned here. Next we are going to see the dimensions associated with the three-phase core type transformer. The overall height of the transformer frame remains the same, the relation remains the same, just like that in the case of a single phase core type transformer. Even the relation of center to center distance between two cores, that is capital D, small d, and WW, that is the width of window, this relation also remains the same, and the depth of the yoke is same as that of the width of largest stamping, since the core which is being used here is of cruciform type. In the case of three-phase core type transformer, there will be two windows. The construction of this three-phase core type, three-phase shell type and all were already discussed in the previous video sessions. That is the first video session associated with the design of transformer. So definitely there are two windows. So just like how I mentioned in the last slide, the width of the window will be the distance between these two circumscribing circles. Please be very careful with that. The overall width of the transformer frame is represented here as W. We very well know that the center to center distance between these two cores is capital D, and the center to center distance between this core and this core is also capital D. So the overall distance from this point to this point will be D plus D, that is 2D. But while finding the overall width of the transformer frame, we have to find the distance between this point and this point. So now we know the distance between centers of the first core and the third core is 2D, and this will be indicating the width of largest stamping, which is represented as small a, that is this length actually. Okay, so half of this will be a by 2. So this much portion is a by 2. Similarly, this much portion is also a by 2, and the center to center distance between this limb and this limb is 2D. So we can write the overall width of the transformer core as a by 2 plus 2D plus a by 2. That is, I can write it as 2D plus a by 2 plus a by 2, which is same as that of 2D plus a. You don't have to by heart all these relations, you just need to know how to draw this diagram, then you can easily write the relations associated with it. So far we have seen core type transformers. In the case of core type transformers, the windings were actually concentric with each other. Now coming to the shell type transformer, in the case of a shell type transformer, these windings are actually sandwiched. That is, both the low voltage windings and high voltage windings are sandwiched between each other. You may refer the first video session to get the distinguishing features between core type and shell type transformer. There it's very well explained that in the case of a shell type transformer, the width of the central limb will be twice that of the outer limbs. That can be clearly seen here. This is actually the width of outer limb. These two are outer limbs, and this is the width of central limb. It is actually twice that of the width of outer limbs. This portion is the window. Both these are the windows of the transformer, and the shaded portion is indicating the windings, both primary and secondary windings. Horizontal cross-sectional view is also shown here. Unlike core type transformer, there is no concept of circumscribing circle. Therefore, we can take this whole portion as the width of window. See, this is the width of window from this point to this point, and this is actually the height of window. The core which is being used here is a rectangular core. In the case of a rectangular core, the height of yoke, that is this portion, is indicating the height of yoke. It is same as that of the width of rectangular stamping, that is HOE is equal to A, and the depth of yoke, it is indicated here. This is actually the depth of yoke. It is same as that of the depth of core, as the core which is shown here is rectangular in shape. The overall height relation remains the same as that of the core type transformer, but instead of HY we can make the substitution of small a, so the relation gets modified into H is equal to HW plus 2 small a. Now let's find the overall width of the transformer core. The overall width is from this point to this point, so this much is actually small a, and this is width of window, and this portion is indicating 2 times small a, and this is also the width of window. So the overall width of the transformer core can be written as small a plus WW plus 2a plus WW plus small a. That is same as that of 2 times WW plus 4a, that is mentioned here. With that, we are completing the dimensions of different types of transformers. Next, we are going to follow a particular set of steps which must be used to simplify the transformer design. Rather than simply saying these steps, we will look into a numerical problem and we will analyze each step in detail. In this problem, you are asked to find the dimensions of core and yoke for a 200 kVA 50 Hz single phase core type transformer. Okay, the type of the transformer is single phase core type transformer. For all such sort of problems, you must draw the diagram which we have said before. It's clearly given that the core used is cruciform core with the distance between adjacent limbs. There is a center to center distance between adjacent limbs is equal to 1.6 times the width of core laminations, that is 1.6 times small a. Assume voltage per turn, there is 14 volt. Voltage per turn is actually ET. Maximum flux densities value BM is given, window space factor KW, current density del, and stacking factor 0.9 is also mentioned. Net iron area is 0.56 d square in cruciform core, where d is the diameter of the circumscribing circle. Also, the width of largest stamping is 0.85 d. A is given as 0.85 d. All the given parameters are mentioned here. Now let's look into the steps. The first step is we have to calculate the value of EMF per turn using the formula ET is equal to K into square root of Q. We have already studied the derivation of this relation and the problem associated with this. But in this problem, the value of EMF per turn is already given, so you don't have to find it out. So we can skip the step 1. Now by using the step 2, we will find the value of AI. The step 2 is the relation for EMF per turn. We all very well know that it is 4.44 F phi m, and for phi m you can make the substitution BM into AI. So from this relation we will be able to calculate the value of AI. So step 2 is performed here and we have find out the value of AI as 0.057 meter square. Next we have to determine the diameter of circumscribing circle. The diameter of circumscribing circle is indicated as small d, and it can be found out from the relation AI is equal to Kc into d square, where Kc is core area factor. This relation we have studied in the last video session. In the case of this cruciform core, The value of Kc is 0.56 and it's also given in the question too. So by using this relation we will be able to determine the diameter of circumscribing circle, and it is found out to be 0.319 meter. In the next step you are asked to find the width of window. The width of window can be easily calculated from capital D and small d. See, this is the diagram of single phase core type transformer. In this problem you must draw this diagram and write down these relations. It's clear from this relation that WW, that is width of window, can be found out by subtracting small d from capital D. So in the next step we will be finding the value of width of window. The steps shown here is not in the same manner how I have written there, but I will be explaining following these steps. So far we have determined the value of AI and small d. The next step there was to find the value of width of window. Width of window can be easily found out from the relation capital D minus small d. In this problem it's very clearly given that capital D is equal to 1.6 times small a and small a is equal to 0.85 times small d. The value of small d has been determined, so you can easily find the value of small a, and after making the substitution of small a here you will be able to get the value of capital D. Once after you know the values of capital D and small d, you can easily find the width of window by making the substitution here, and you will get the value here as 0.114 meter. In the next step we have to find the value of window area. Window area is indicated as AW. It can be easily found out from the relation of output equation of both single phase transformer as well as three phase transformer. In our case it is actually a single phase transformer, so we can determine the value of AW by using this relation. All the parameters BM, KW, del, AI has been determined. Value of AW is unknown. Value of Q is given as 200 kVA. So the only one unknown is AW, which can be easily determined from this relation as 0.0299 meter square. In the next step we will determine the height of window, because we have already found out the area of window and width of window, from which we can easily calculate the value of height of window. That is HW is equal to AW by WW is equal to 0.261. In the next step we will determine the overall height and overall width of single phase core type transformer using the standard relations. In this problem the standard relation is H is equal to HW plus 2HY. While seeing step 7, it's very clear that the area of yoke is taken as 15 to 25% larger than that of the core area in the case of hot rolled silicon steel transformer. And if CRG is used, then the area of yoke is considered to be AI divided by 0.9. That is, if CRGO is used, then the area of yoke is same as that of the area of iron core. If no specific mention is given about the material which has been used for yoke in the question, you can consider it as a CRGO on. So the standard relation for overall heights get modified into capital H is equal to HW plus 2 small a instead of 2 HY, that is height of yoke. Now you can make the suitable substitution for HW and A, and you can easily calculate the value of capital H. And the standard relation for overall width in the case of single phase core type transformer is D plus A. Give suitable substitution for capital D and A, you will be able to get the overall width of the transformer frame. So we have determined the overall height and overall width, that is the overall dimensions of this particular type of transformer. In the same manner you have to follow the steps which are given before, and you have to solve this problem. The type of transformer which is given here is actually 3-phase core type 1. The very first thing which you must do for this type of problems is you have to draw the corresponding vertical cross section diagram as well as horizontal cross section diagram, and you have to give the proper markings. Then only you will be getting the complete marks while solving this problem. Hopefully the dimensions of different types of transformers are very clear for you. All of you must learn to draw these diagrams, then only you will be able to solve the problems associated with it. You don't have to by heart these relations. If you know how to draw these diagrams clearly, or if you have understood this concept clearly, then definitely you will be able to write the relations from this diagram itself. Both single phase core type and shell type transformer, as well as three phase core type transformer. The dimensions of these three type transformers are very important. Generally, essay questions are being asked from this region. With that, we are completing today's session. In the next session, we will study about the design of windings. Thank you.